Dear friends, in our previous presentation, we have seen the working of the binary weighted register type of digital to analog converter. Though it is very simple, we have seen what are its limitations, right? When the number of bits are increased, too many numbers of the resistance resistors are required, which is very difficult to realize, right? So therefore, they are generally limited to a lower bit DACs, 3 bit or something like that. Even there also, it is very high, the resistor requirement. So in order to overcome that particular problem, we are making use of another type of DAC that is called as R to 2R ladder network. The very R to 2R itself indicates that there are only two types of the resistance, or the two values of the resistance required, right? So now let us try to see how exactly we will be able to realize the R to 2R ladder type of network. Digital to analog converters, right? So please have a careful observation of this particular diagram, right? All the side rungs are having R, all the central rungs are having 2R, you can see here. So this is basically a 4-bit, right? This is a 4-bit R to 2R ladder type of uh, digital to analog converter, right? Now you have, as usual, you have your operational amplifier, which is connected in the inverting mode. You have got the feedback resistance here. This is the load resistance, where you take the value of your V0 here. Okay, then you have got 4 switches here. Basically, I am taking an example of a 4-bit R to 2R ladder type of digital to analog converter. B0, B1, B2, B3. B3 is my MSB and B0 is my LSB. Okay, so accordingly, these bits, okay, the switches, the digital switches, can either be connected to a logic high or logic zero, what you can see here. In our earlier representation, when we have taken about the binary weighted resistor type, this VR we had taken as negative, if you remember properly. So now here I have deliberately taken it as positive, so that the direction of flow of current would be this way rather than it is going in the other way around, right? So in order to have the both type of examples, I have taken this deliberately as plus VR. So what I mean to say here is a particular switch could either be connected to a logic high in terms of plus VR, or it can also be connected to ground here. And now with this particular introduction, let us try to see how exactly your R to 2R ladder type of network digital to analog converter works. Okay, now let me go to the next slide, wherein I will show you both the diagrams. One diagram we have already seen in our previous slide, and this is going to be the equivalent circuit for one particular bit position. That means when your B3 is connected to VR, as we have seen in the previous case. Okay, now let us say that your B3 is connected to VR and all other bits B1, B0 and B2, they are connected to ground. So when this is the case, we will have to see how your circuit looks like in the form of Thevenin's equivalent. If you look from this particular point, so this is going to give you the Thevenin's equivalent, okay, which I have represented here as RTH, and the other part of the network you can see here 2R is here, right? Your B3 switch is connected to VR here. So this is what is the circuit, okay, and this is VID. So the virtual ground concept, there will not be any current here. So whatever the current you are having, the same current will be flowing through the RF here, right? So now if you look at the Thevenin's equivalent circuit, so this is going to be the Thevenin's equivalent resistance. If you look beyond this particular point, though it appears to be little lengthy, it is very simple. You can see here this 2R and this 2R are in parallel, that is in series with this R, okay, that is again in parallel with this 2R, then that is again in series with this R, right, that is again in parallel with this 2R, then finally that is in series with the last R here, right? So in this way you have the equivalent network, and you can see here this 2R and 2R will give me R, R plus R is 2R, then again that is in parallel with 2R, that is again that is going to give me R, R plus R 2R, 2R and 2R in parallel R, then finally that is added with R. So the equivalent resistance here is going to be 2R. The Thevenin's equivalent resistance is going to be 2R here. Okay. So now if you take, for example, R is equals to 10K and 2R will be 20K. So your IRF, this particular current, will become VR divided by 2R. If you take VR as 5 volts, so the current here will become 0.25 milliampere, right? So now if you take V naught here, the current when it becomes 0.25 milliampere, for this particular case of B3 connected to VR, and when all the other switches are connected to ground, your V naught will become 0.25 milliampere into the RF value with a minus sign. So that will give you the voltage equal to VR is equals to minus 5 volt for that particular case. Okay, like that you can have all the switches connected to either logic high, that is VR, or ground, and for all the 16 combinations, that is 0 0 0 0 2 0 0 0 1 and so on and so forth up to 1 1 1 1, you can estimate the value of V naught by means of a generalized equation. You can see here that equation becomes V naught is equals to minus RF into B naught divided by 16R plus B1 divided by 8R plus B2 divided by 4R plus B3 divided by 2R. So this is only for 16-bit DAC. Okay, so as the bits change, this also is going to change here. This is not the general equation. This is the specific equation for a 16-bit DAC. Okay, now depending upon a particular bit is connected to logic high or logic low, you can either include it or exclude it, right? And you are going to get the value of V naught. If you draw that, so you can see here the plot here is going to be on the other side, as we have seen in the case of the binary weighted type, where we had taken our reference voltage VRS minus there we had got this graph something like this. If you had remembered it properly, you will be able to recall it. And in this case, I'm going to get it in this direction, in the negative, with the negative slope, right? And for B0, B1, B2, B3 being 0, your output voltage is going to be 0, 0, 0, 0, 1. That is, this is MSB, this is LSB, this is going to be minus 0.625. If you substitute that in this equation by taking VR is equals to, so this is, sorry, this should be multiplied by VR. Please make a small change here, right? This whole equation should be multiplied by VR, otherwise there is no voltage parameter here. Whole equation should be multiplied by VR. Okay, please make the necessary changes here. So then for 0 0 1 0 you will get minus 1.25. We have seen one of the values, that is 0 0 1 0 0 0. If your MSB B3 is connected to high, then you are going to get it as minus 5 volts. In the previous slide we have seen. So like that, when all the bits are 1 1 1 1, you are going to get this as minus 9.375 volts. So this is what is the different, the analog output values you are going to get proportional to the input digital bits or the binary bits. So now the very advantage of this particular circuit is, irrespective of the number of bits that you are going to use here, you need only two types of resistors, right? Values. One is R and another is 2R. Of course, the connection complications will be there, right? As you go with the higher bits, you need to have too many number of R's and 2R's to be connected. But this is going to give you a better, economy or viability, right? So compared to its counterpart, that is the binary weighted resistor type of DAC, right? So again, if you look at the resolution here, right, as long as you take R is equals to RF here, you will get the same equation what we have taken for the case of binary weighted type of DAC. Okay, V is equals to 1 divided by 2n into VR divided by R into RF. So if you take these two are equal, then it is again going to be VR divided by 2 to the power of n. So the resolution equation or the formula for the resolution remains same. So now these are the two types of resistors, right? Or sorry, two types of the digital to analog converters. One is called as the binary weighted resistor type, right? Where each bit is given a certain binary weightage, and accordingly you are going to get the analog output. Whereas in the second type you have got R2 to R ladder network type, wherein only two values of the resistance are required to realize the operation of digital to analog converter. In both the cases, your output voltage will be proportional to the input digital bits. Okay, input digital bits. That is how you are going to get the output voltage in the analog form. So the input bits are going to be converted into the output voltage. This is the basic functionality of digital to analog converter, right? So in our next presentations we will see its counterpart, that is the ADC, the analog to digital converter. This is also an equally important component in our digital system or the instrumentation. How exactly an ADC is realized, that we shall see, and what are the different types of the analog to digital converters, the working principle of analog to digital converters, we shall see in our subsequent presentations.